Today we're setting our sights on a planet that's often overlooked, a tiny, scorched world dancing closest to our sun, Mercury. Imagine a place of extreme contrasts. On one side, temperatures soar to a blistering 430 degrees Celsius, hot enough to melt lead. Yet, in the permanent shadows of craters near its poles, temperatures plummet to a mind-numbing -180 degrees Celsius. It's simultaneously one of the hottest and coldest places in our entire solar system. For decades, we saw Mercury as little more than a desolate, cratered rock, a cosmic relic baked and battered by its proximity to the sun. But beneath that seemingly barren surface lies a profound and long-standing mystery, a puzzle that has left astronomers scratching their heads for generations. What if I told you that this tiny world is hiding secrets that could rewrite our understanding of how planets form? Why are scientists suddenly so excited, pouring resources into new missions to this celestial enigma? Stick around because we are about to peel back the layers of Mercury and uncover the astonishing anomalies hidden within its core. The biggest surprise Mercury has thrown at us is its sheer density. For a planet so small, it's only slightly larger than our own moon. It's incredibly heavy. In fact, after Earth, it's the second densest planet in the solar system. This points to something extraordinary. Mercury must have a massive, iron-rich core. Current models suggest its core makes up a staggering 85% of the planet's radius. To put that in perspective, Earth's core is only about 55% of its radius. This is a planetary-scale anomaly. It's like finding a cherry with a pit the size of a peach. It just doesn't fit the standard models of planet formation. So how did this happen? The leading theory for a long time was the giant impact hypothesis. The idea is that early in its history, a proto-Mercury was struck by a massive planetesimal, a planetary embryo. This cataclysmic collision would have been so violent that it stripped away most of Mercury's original rocky mantle and crust, leaving behind the dense, oversized iron core we see today. It's a dramatic and compelling story, a cosmic hit-and-run that fundamentally altered an entire world. The debris from this impact would have been blasted into space, leaving Mercury as a shadow of its former self, a core with a thin veneer of rock. But as compelling as that sounds, it's not the only theory on the table. Another idea is the evaporation hypothesis. This theory suggests that in the very early days of the solar system, when the sun was much hotter and more powerful, its intense radiation and solar wind simply blasted away Mercury's lighter, outer layers. Being the closest planet, it would have borne the full brunt of our young sun's fury. Over millions of years, the rock and silicate material were effectively sand-blasted into space, leaving the heavier, more resilient iron core to dominate the planet's composition. It's a less violent but equally transformative vision of Mercury's past. And there's even a third possibility, one that ties into how the solar nebula itself behaved. Perhaps the region where Mercury formed was naturally enriched with heavier elements like iron. The swirling disk of gas and dust from which the planets coalesced wasn't uniform. Magnetic fields and the sun's heat could have sorted the materials, causing lighter, silicate materials to be pushed further out, while heavier metallic elements concentrated closer to the sun. In this scenario, Mercury didn't lose its mantle. It just never had a large one to begin with. It was simply built from denser stuff. For decades, these were just theories, elegant ideas with little hard evidence. We had data from Mariner 10 in the 70s, and the Messenger spacecraft which orbited Mercury from 2011 to 2015. Messenger gave us our first truly global look at the planet, confirming its weird composition. But Messenger also raised new questions. It discovered surprisingly high levels of volatile elements like potassium and sulfur on the surface. These are elements that should have boiled off and escaped into space in either a giant impact or a solar evaporation scenario. So what's going on? How can a planet that was supposedly cooked or smashed to pieces still retain these delicate, easily vaporized materials? This is where the excitement really begins. We are in a new golden age of Mercury exploration, thanks to a mission called BepiColombo. This is a joint venture between the European Space Agency and the Japan Aerospace Exploration Agency. It's not one but two orbiters traveling together, each packed with state-of-the-art instruments designed to answer these very questions. BepiColombo will map Mercury's surface and magnetic field in unprecedented detail. It will analyze the composition of the surface with incredible precision, looking for clues about its origin. One of its key goals is to determine the exact size and state of Mercury's core. Is it entirely liquid? Or does it have a solid inner core, like Earth? The answer to that question is crucial. A liquid outer core is what generates a planet's magnetic field, and surprisingly, Mercury has one. It's weak, only about 1% as strong as Earth's, but it's there. Understanding how this tiny, slowly rotating planet can sustain a magnetic field is a major piece of the puzzle. A magnetic field acts like a shield, protecting the planet's surface from the harsh solar wind. It might even be part of the reason those volatile elements manage to stick around. BepiColombo's magnetometers are far more sensitive than any that have gone before, and they will give us the first three-dimensional map of Mercury's magnetosphere. Another incredible discovery that BepiColombo will investigate further is the presence of water ice. Yes, you heard that right. Ice on the hottest planet. As we mentioned earlier, the poles of Mercury have craters that are in permanent shadow. In these frigid traps, temperatures never rise above freezing, allowing water ice to remain stable for billions of years. Messenger confirmed the presence of this ice using radar and neutron spectrometry. BepiColombo will take a closer look, trying to determine the quantity and purity of the ice. Where did this water come from? Was it delivered by comets and asteroids, or could it have outgassed from the planet's interior? The answer could have profound implications for how water is distributed throughout the solar system, and even for the origins of water on Earth. Beyond the core and the ice, BepiColombo will also study Mercury's hollows. These are strange, shallow, rimless depressions found all over the planet, often with bright material inside. They look like parts of the surface are simply vanishing into thin air. Scientists believe these hollows are formed by the sublimation of some volatile material in the rock, which turns directly from a solid into a gas when exposed to the harsh solar environment. This is an active geological process happening right now. By studying the hollows, we can learn more about the volatile materials that are locked away just beneath Mercury's surface, another clue in the mystery of its formation. So, Mercury is not the dead, static world we once thought it was. It's a dynamic planet, with a mysterious past and an active present. Its oversized core challenges our models of planetary formation, forcing us to consider violent impacts, intense solar radiation, and the very chemistry of the primordial solar system. The presence of both volatile elements and water ice seems to contradict the story of a world that was baked and stripped bare. It's a planet of contradictions, a puzzle box waiting to be opened. The data that BepiColombo will send back over the coming years promises to be revolutionary. It will either provide strong evidence for one of the existing theories or, perhaps even more excitingly, force us to come up with entirely new ones. By understanding how this strange little world came to be, we gain a deeper understanding of the processes that built our own planet and the countless others orbiting distant stars. Mercury, the solar system's anomaly, holds a key to our cosmic origins. The next time you gaze up at the sky, remember that small, swift point of light moving close to the sun. It's not just a rock. It's a planetary detective story in progress, a world of fire and ice with a heart of iron. Thank you so much for joining me on this deep dive into Mercury's hidden depths. If you enjoyed this journey and want to explore more cosmic mysteries with us, be sure to hit that like button, subscribe to the channel, and ring the notification bell so you never miss an update. What do you think is the secret to Mercury's formation? Let me know your theories in the comments below. Until next time, keep looking up.